from yesterday? Revision from yesterday. What's the expected p hat? P. Okay, good. What's variance of p hat? Well, you can say standard deviation of p hat, not necessarily that. Square root p 1 minus p. Shh. We start class, everyone. Okay, so we have expected value and standard deviation for p hat. And p hat is equal to x over n. Well, x is a binomial distribution. N is the number of sample and p is the actual population proportion. That's what we learned yesterday. And I said, well, even though it's not 100% accurate, but we think this is accurate enough because from a large population, if we withdraw someone from that, we almost say there's no change for the next selection about the successful rate. So we use a binomial to calculate p hat values. Well, you can see for the previous examples, we don't use p hat, we use the x value. We convert the p hat into x, the number of success, and then we use binomial distribution to do the probability. Do you remember what we learned in the last chapter, like chapter 16 for the normal chapter? What's the last exercise we did? Anyone remember? The last exercise, well, the last page of chapter 16 knows what we have done. Yeah. Yeah, binomial approximation, right? If this distribution is a binomial distribution, and when that satisfies np is greater than 5 and n times 1 minus p is greater than 5, we said it's good enough to do an approximation, and the approximation is approximate to normal distribution. And I also said all the distribution, when the number get large enough, everything will look like a normal curve, like a bell curve shape. So in this question, we can do similar thing as well. Well, p, you know, we can sketch for p, we can get when x equals to 1, p hat equals to that, and then we have a probability of achieving that p hat. When x equals to 2, what p hat is, and what's the probability of getting that? Well, the probability is calculating by using the binomial PDF. And p hat value is calculated by x over n. I can plot all the dots. Well, it's not necessarily exactly looks like a binomial distribution, but it's still all the dots. Can you think about that? It's all the dot values because I use x values. So we have 3 rows. The first row is a x value, like the number of success. Well, it can be 0, 1, 2, ... And then the next row will be the p hat value, which is x over n. That can be 0, that's 1 over n, that's 2 over n, and 3 over n, and then we have some values for p hat. That's the sample proportion. And I can have probability that the p hat equals to lowercase p hat. I use the binomial PDF. I use the first row success number to calculate them. And then I can plot these 2 rows, like when p hat equals to 0, probability equals to that. Well, for example, probability equals to 0, p hat equals to that. When p hat equals to 1 over n, the probability is there. When the proportion is 2 over n, the p hat is somewhere there. And then we can keep plotting them like for different places. And then when n get large enough, we have a really large number. Again, like even though I'm not sure if it's a binomial distribution, but again, as I said, all the distribution, when number get large enough, they all looks like a normal distribution shape. Remember that? Like in the end, when they get really close to each other, we have many, many points, they're next to each other, then we can almost see it's like a connecting curve. It's more like a continuous curve, and you will have just a normal shape, like the bell curve. So that's the point I want to make here. In the previous exercise, we used binomial distribution to calculate p-hat. But when n get large enough, when your sample is huge, like I can take a sample of 20, I can also take a sample of 200. When the sample is large enough, like we can use normal approximation to do that. But you do normal approximation only the question asks you to do that. Okay, well, only the question mentioned use normal approximation to calculate the sample proportion is in between what and what. Then you use approximation. Otherwise, when we say nothing, we assume we use binomial. Or if the number is really small, like the total is given, then we use the NCR, like the hypergeometry one. Otherwise, we don't use normal, okay? We don't use normal unless the question mentioned that. So what I can write here is p-hat is a random variable. I'm not going to convert that into x. I don't care about x now. What I will do is I will say, well, I shouldn't write approximate, well, but let you know that's approximate distribution. Approximate to a normal distribution. Okay, again, everything looks in like a normal in the end. With mu. Mu is what? Mu is p. Okay, because the expected p-hat is what? It is p. Okay, it is p. And then with the standard deviation is p1 minus p over n. And then we need to square that because it's the spot for variance. That's it. Okay, that's all you need to do. You still need to know the formula for expected p-hat and variance p-hat. But we can easily just write that into a normal distribution when it asks you to do a normal approximation. Same mu, same standard deviation, but we put that into a normal curve. And what's the domain for p-hat now? What's the domain for p-hat? R. Okay, it's not 0 to 1. Normal proportion should be in between 0 to 1. But in this case, if it's a normal distribution, we always assume it's negative infinity to positive infinity. We do not think about the practical domain. So this is the distribution. Okay, let's have a look at one question here. For example, 8. Assume that 60% of people have a driver license. Find the exact probability that in a random select of sample of 200. Okay, this is n, a sample of 200. More than 65% of the people have a driver license. Okay, in 200, how many people have driver license? I want more than 65%. So what I will say first is in A, let X be the number of people have driver license. X is a binomial distribution with 200 trials and 0.6 successful rate, because assume that 60% of people have driver license, so successful rate is 0.6. Also, I know p-hat equals to x over 200. Okay, number of success over 200. More than 65% of the people have driver license. So in the sample, so the sample proportion needs to be greater than 65%. Okay, then what we should do is the probability x over 200 should greater than 65%. If you times 200 on both sides of the inequality, we have x greater than 130. Okay, in this 200 people, you need to have at least you need to have more than 130 people who have driver license. Then we can have a proportion more than 65%. So 200 times 0.65, we have 130. So after this is a binomial CDF, because you know we are talking about x instead of talking about the p hat. Well, this is the exact distribution, so we use the binomial to do the calculation. If you go menu 55B, because it's more than something, I have 200 trials. Successful rate is 0.6. What's my lower bound? 131. Okay, it's not 130. It needs to be more than 130. The next integer is 131. What's the upper bound? 200. Correct. 200. Okay. Click enter. We have 0.0639. Let's give 4 decimal places. 0.0639. Okay, that's the probability. This is a quite exact probability. Okay, it's a quite exact probability. We use rounding to do that. Not rounding, the binomial to do that. And if you look at the next one, using the normal approximation, okay, it will clearly state that, then you use that. Okay, use the normal approximation. Find the approximate probability that in a random select sample of size 200, more than 65 people will have driver license. Well, it will be exactly the same question, but use another way to calculate. So what we should do is we change distribution. Before we use X, use as an exact probability, but now we want to approximate. We directly use p hat to do the calculation. So for B, more than 65. Well, first of all, I know expect p hat is just, what's expect p hat in this question? Yeah, what's P? 0.6, okay, not 0.65, it's 0.6. And the standard deviation of p hat is square root of 0.6 times 0.4 over 200. That's that divided by that. And approximately that. Well, I just keep this first. I will just exactly type that in. So p hat is, because I can use approximate. Okay, everyone, you don't need to write that. Okay, when you do approximate, you don't need to do that. I just write it to mention that this is not exact. It's approximation. Is a p hat is a normal approximation with the same mu as before and same standard deviation as before. And then after I know the distribution, we're just looking for p hat is more than 65. I can write 0.65 actually, but p hat is more than 65%. And I just use calculator directly. I don't care about what is X. Because it's a normal, I use 552 for normal CDF. The lower bound is 0.65 because it's 65%. What's my upper bound? Infinity. Okay, it's not 1, it's infinity. Okay, mu is 0.6, that's what we calculate, and square root, sigma square root 0.0012, that's the square sigma value. Okay, just enter whatever I should enter. Because p hat is a normal approximation, I'm looking for p hat is greater than 0.65. What's the probability? Directly type into the CAS. Okay, that's 0.07. Well, if you give 4 decimal places, is 0.0745. If you compare with the exact value, you can see that's about 1% difference between them. It's quite huge. The successful rate for the success rate here is only 6.4%, and you have 1 point something difference. Is quite huge because two reasons. First of all, it's not the correct method, and second is n is not large enough. Okay, and 200 is not good enough. I think if you change that to 2000, it will be much better. Okay, answer will improve a lot. Okay, so that's just for using a normal approximation. Let's have a look at the next one. Well, you do the next one by yourself, and then in the end we check answer together. It's just exactly the same thing compared to the first one. Okay, for this one, the proportion of voters in population who favor candidate A is 52%. Obviously, that's the p-value. That's from the big data, like I work out over this many people. We have 0.52 of supporting candidate A of a random sample of 400. Okay, 230 indicate they would vote for candidate A at the next election. So this is a sample, it's a fixed sample already, and I know exactly the number of people who will vote for A. So A is asking, what is the value of the sample proportion p hat? Can you see this p hat is a lowercase p hat? Okay, it's a small p, it's not a capital P. Why this is a small p? Because for each sample, the proportion is a fixed value. It's not going to vary. What I talk about that I'm going to take a sample of 400. In this case, my p hat is capital because my x, I don't know what I will get. It might get 0 vote for A, or I can get 400 vote for A, or I can have 230, I can have 270. Like, I don't know yet. So at this time, I have capital P hat. But already I know what I have. I already know what is involved. There's 230 people will vote for that. Then I know this is a lowercase p hat. So for this particular sample, my lowercase p hat is a value. For this value, that equals to 230 over 400. And that equals to 0.575. Well, you can leave in fraction, doesn't matter. Okay, that's it. For B is asking find the approximate probability. Okay, you see the word approximate? Normally they will make it more specific, like use the normal approximation to find what. So this is like a normal approximation question. So approximate probability that in a random sample of 400 voters, the proportion who favor candidate A is greater than or equals to the p hat observed in a particular sample. So I want to be more than 0.575. So what I was thinking about is the expect p hat that equals to 0.52. Okay, equals to p, and then the standard deviation of p hat that equals to square root of 0.52 times 0.48 over 400. I don't know what is it. I can just type that in. 0.5. How I open this one? 0.52 times 0.48 divided by 400. Well, I'm not going to solve for it. Just define about like A. Okay, so let's say that's A. Now what I'm going to do is state the distribution for P. P is a normal distribution, approximate, okay? It's not exact, it's approximate normal distribution with the same mu and same standard deviation as the exact distribution. Mu and standard deviation, okay, mu and standard deviation. And then what I'm looking for is the probability that my p hat is greater or equals to 0.575. Okay, p hat is greater than 0.575. I can go menu 552, menu 552, normal CDF, lower bound is 575, upper bound you should use infinity. Mu is 0.52 and standard deviation is A. Okay, standard deviation is A. Okay, the probability we get is 0.0138. 0.0138. Oh, I can put a 4 there. Well, this is the approximate. Okay, this is the approximate probability. But if you can think about the exact probability, you say X is the how many people in 400 sample will vote for candidate A, and that's a binomial distribution with 400 trials and 0.52 of the successful rate. So P hat is X over 400. What you're looking for is the P hat greater or equals to 0.575. And that equals to probability X is greater or equals to 230. Now, because P hat is X over 400, we times 400 on the other side, is X greater than 230 or equals to 230. And I can use binomial CDF to work on that. I have 400 trials. Successful rate is 0.52. Lower bound is 230 and upper bound is 400. Okay, more than that. It can be 200 equal or above. Press enter in. I have 0.01555. This is like better. Okay, this is a bit better, but not 1 to 0.2% difference. Okay, 0.2% difference. You can see like when we increase the numbers, the result gets better. Yeah, that's just one for exact and one for approximation. Which period we have class tomorrow? 2. Okay, good. Why are we so exciting? I think we can finish tomorrow if it's a 70 minutes lesson. I'll try to finish confidence interval tomorrow. Okay, so I'll just stop here for today. That's just the 3 method. Think about the 3 method we learned, how to calculate sample probability for sample proportion. Okay, first 2 are discrete and the last one is continuous. Okay, the first 2 are discrete because they are in tables. Binomial is discrete as well, and the last one is use normal is continuous. Okay, have a think about that, and tomorrow we'll do confidence interval.